Today we're going to first finish up our discussion from yesterday. Yesterday we were discussing propagators in the free scalar field theory. And then we'll move on to begin our discussion of interacting scalar field theories. And the objects we'll be interested in computing will be cross-sections and decay rates. Those are what we can physically measure. And so today we'll begin a several lecture journey of learning how to compute these observable quantities, the cross-sections and decay rates. And at the end, we'll see that these are related back to the propagators that I'll begin today's lecture by discussing. So we left off, we deduced a formula for the, what I call delta R, which was related to the expectation value of the commutator and we found a formula for it that was in terms of a four-dimensional integral over complex contour in the P0 plane. And this contour avoided the two poles in the complex P0 plane. So this, we can rewrite I over P squared minus M squared as I over P0 minus K, the three vector P squared minus M squared, which is, this is I over P0 squared minus P squared minus M squared, which is I over P0 squared minus EP squared. So that there are poles at plus or minus EP in the complex P0 plane. And this contour avoids those poles by going above them. And the way we derived this was we said that, so if x0 is greater than y0, then because of the minus I here, we should close the contour in the lower half plane. And we'll get contributions from both of these poles. And we related that back to our expression for this commutator. And if y0 is greater than x0, we should close the contour in the other half of the plane. And we don't enclose any. The new semicircle doesn't contribute. And so the integral along this contour is just 0. There's no poles enclosed. So that's where we left off yesterday. Are there any questions on that before we continue? Okay. So this object we've been studying is, in fact, a Green's function for the Klein-Gordon operator. And it's what's known as the retarded Green's function, which is what the R here stands for. So we can use it to solve the classical Klein-Gordon equation, where we want to impose some boundary conditions in the past and evolve forward. So we can let's see why it's a Green's function. So if it's a Green's function, then if we act with the Klein-Gordon operator, p squared plus m squared on delta r, And let's suppose this derivative is acting with respect to x instead of y. Then we get this expression. This derivative, when it acts on the exponential, will just bring down factors of minus ip. So we'll get a minus p squared, m squared, e to the minus I p dot x minus y. And this cancels out. Just left over with a factor of minus I. And then this exponential. And this is a familiar integral, one you did several times in tutorial yesterday. So this is just a delta of x minus y, four-dimensional. So it's a Green's function. So Green's function should be proportional to the delta if we act with the operator on them. Is just a choice of normalization. And so we see this is a Green's function. It's a retarded Green's function because it vanishes for y naught greater than x naught. And we can then use this to solve the Klein-Gordon equation with a classical source. So if we wanted to solve this equation, we could do that using the familiar method of Green's functions. That's, for the most part, not going to be our interest in this course. But a closely related object to this delta r will be very important moving forward. And so it's useful to look at this derivation and note that in no point did we actually use the particular choice of contour here. So contour should still be here, but in this line, there are no poles. So it doesn't really matter if we go above the poles or below the poles or some combination. So we can choose any contour that's close to a contour along the real line and just avoids these poles in some way. And those will be other Green's functions for the Klein-Gordon operator. So in particular, so in classical physics, the retarded Green's function and the advanced Green's function are the most interesting. If we want to impose boundary conditions in the future, we'd use the advanced Green's function. The advanced, all we need to do to change the retarded Green's function into the advanced Green function, it's just go around these poles in the opposite direction. So if we went below both of the poles, we would get went below both of the poles, using P, like this. This is the advanced contour, and so the advanced propagator would be the same integral, just with the advanced contour. And the same arguments as before tell us that this should be equal to the expectation value of the commutator for x naught less than y naught, and it should be 0 for x naught greater than y naught. Exactly the opposite of the retarded contour. retarded Green function. Most useful one for us will be a different choice of contour. So for us, delta f of minus y, known as the Feynman propagator, is defined to be time-ordered expectation value. Will be the most useful. So here I've introduced a new symbol. So this is the time ordering symbol. And it means take all of the operators that follow and move the latest one to the left and the second latest next, and all the way on to the earliest operator on the right, latest to the left. So in this case, this is equal to if x naught is greater than y naught, we need to put 5x will be the later operator, 5y will be the earlier operator, and if y naught is later than x naught, then we need to put the operators in the other order. And this is equal to an expression that's almost exactly the same as the expressions for the retarded and advanced propagators, just the contour is different. And the Feynman contour avoids the poles as follows. So it goes below the pole at minus EP and above the pole at plus EP. And this is often abbreviated as just doing a real integral for P naught and changing the location of the pole by a small amount, putting a plus I epsilon here. And so these mean the same thing. So if we put a plus I epsilon here, we could do this by, so we'll basically shift this pole downward and this pole upward, and then we integrate along the real line. This would be a pole at EP minus I epsilon, and this would be a pole at minus EP plus I epsilon. So we can then just integrate along the real line, and we'll get the same thing if epsilon is infinitesimal. And so this result, so this is equal to Feynman propagator, x minus y, and this is the most important result from our discussion of the free Klein-Gordon theory, free scalar field. We're going to come back to this, and this will be one of the building blocks of perturbation theory. So we're now going to spend several lectures discussing how to compute cross-sections and scattering amplitudes. In the end, we'll be able to relate those things back to Feynman propagator. Yes.
So this time ordering thing you're doing, it doesn't result in any like Lorentz invariance issues because you're using some specific times.
Specific. No, it won't result in any Lorentz invariance issues. you might worry if we've seen that preservation of causality basically means that our commutators have to vanish outside of the light cone. If they didn't vanish, then we might be changing things with the time ordering, but we'd have bigger problems than that because we wouldn't have causal theory. So. Other questions? Okay, so now we're going to begin our discussion of interacting theories. And our goal will be to compute cross-sections and decay rates. And so before we begin and try to do that, I just want to give you an overview of where we're going over the next few lectures. So our main goal will be to compute cross-sections and decay rates. These are quantities that can be directly measured and are the main objects of interest in high-energy physics. And so for concreteness, we're just going to learn how to compute these things. But many of the techniques I'm going to describe that we're going to use to calculate these things are also of interest and of use in other fields of physics, for instance, in condensed matter physics. We can compute other observables. Most of the same techniques will work, but just for concreteness, we'll focus on computing these two objects in this course. And we're going to do this in steps. So today, what we're going to do is relate these observable objects, the cross-section and decay rate, to scattering amplitudes. So what this is an expression in the Heisenberg picture. So we can imagine in the Heisenberg picture we've got some initial state, which is time independent. In the Heisenberg picture, we can time evolve it and then compute its overlap with some final state. Or equivalently, this is in the Heisenberg picture. In the Schrodinger picture, we could write this as what we're interested in is some initial state at time minus infinity, and we want to compute the overlap of that state with some final state at time t equals infinity in the Schrodinger picture. And if we can compute this, we can understand all of the dynamics of the theory. So that's that's how far we'll get today. We'll be able to relate these cross sections and decay rates to scattering amplitudes. And then tomorrow, we're going to relate these scattering amplitudes to objects that will look somewhat familiar. We've just seen an example that's very similar. So we'll relate these scattering amplitudes to endpoint correlation functions or endpoint Green's functions. These are different names for the same thing. So in an interacting theory, we denote the vacuum by omega. It's different from the free vacuum in general. It's the interacting vacuum. And we'll do this using the LSC reduction formula. So that will be tomorrow. So we'll start with cross sections, go to scattering amplitudes, then relate those to endpoint correlation functions. And so in order to compute endpoint correlation functions in an interacting theory, the simplest way to do that is to relate these endpoint correlation functions in interacting theories to endpoint correlation functions in a free theory. And we'll do that on Monday. So do this by going to the interaction picture, which is kind of a hybrid between the Schrodinger and Heisenberg picture. And here, this is the free vacuum. And these objects we can compute in much the same way as we did yesterday and today when we computed the Feynman propagator. And so the last step in this chain of logic is we can relate these endpoint functions to the Feynman propagator, which is just a two-point function. And we'll also do that on Monday. That's known as Wick's theorem. And so there are many steps in this process, so I'll remind you periodically of where we're going and what we're trying to do. That's the big goal, is to compute these objects. And then we'll look at another equivalent way that's basically a faster way of going between these two things. So it's a big shortcut, which is the method of Feynman diagrams. That's where we'll be on Tuesday. So it's a lot of steps in the calculation, and please ask if it's unclear how things are related. But this is our long-term goal, is to relate these observable quantities to this function here. Okay. So our goal today is to compute cross-sections in an interacting scalar field theory, or at least do the first step in that chain. And so it's useful to remind ourselves what's meant by a classical cross-section, because cross-sections in quantum mechanics will work very similarly. In fact, we'll take some of the relations we'll derive in the classical theory just as definitions of what we mean by the quantum field theory cross-section. So the type of setup we have in mind is we've got, it'll be convenient to work in a frame where we're colliding two beams of particles. Let's just work in the frame where one of the beams of particles is at rest. So we can imagine we've got some spherical targets here. And these are at rest. And let's call these are spheres of radius r. So cross-section of each one is pi r squared. The geometric cross-section is pi r squared. And let's call these particles of type A. Type A. And let's imagine we're sending some point particles with velocity v. These are type B particles. These will be point particles. At our fixed target. And we'll assume that the densities of both types of particles are low enough that the probability of having multiple collisions is negligible. So we'll assume that each particle of type B can collide either with 0 or 1 of the particles of type A. And let's, so if we're looking down the beam, so this is looking down the beam. Let's assume that the area common to both beams is A. I'll put feet on this one. It's different from this label. And so we've got our spherical targets, which just look like circles from this looking down the beam in this direction. And so we see that the probability that a given particle of type B will collide with a given particle of type A should just be the ratio of the geometrical cross-section of one of the particles of type A to the total area of the beam. So if I ask what's the probability that this particular particle of type B will hit this particular particle of type A, that probability is just sigma over A. And so then the number of collisions will just be the probability that a given particle of type B will collide with a given particle of type A times the number of possible ways to pair particles of type B with particles of type A, which is just the number of particles of type B times the number of particles of type A. And remember, we're assuming the density is low enough that there's no possibility of multiple collisions. So it will be useful to write this in another slightly different way. So you can assume that the time it takes for, assume this beam has a finite length in this direction. Then the length of this beam LB, LB should be equal to the velocity times the time it takes for the beam to pass a particular point. And so then this collection of particles of type B will have some volume. And so the volume of the region of space where the particles of type B are located is LB times A. So we can rewrite this. So this is the number of collisions. As sigma times NB times NA times, so A is equal to the volume over VT. So we get VT over the volume. And so here we've got the way we'll use this is a relationship between the cross-section, the geometric cross-section of our targets, which is a measure of how likely or how strong the interactions are. It tells us something about how likely collisions are to occur, and the probability of collisions. So we'll use it in this way. And so we see that sigma is equal to P times the volume over Vt. And we'll just take this as a definition. So we derive this in classical physics. And we'll take this as the definition of the cross-section in quantum physics. And so we'll say that the differential cross-section is defined to be the differential probability times the volume over Vt. And this differential probability will compute in the usual way by squaring an amplitude. And this is a cross-section in the sense it's a measure of the interaction strength, and it still has units of area. So we'll interpret it in much the same way as a classical cross-section. And we're basically only interested in 2 to n scattering. And that's because it's the probability of colliding 3 particles at once is usually negligibly small. So throughout this course, we'll just focus on the case of 2 initial particles. And in that case, we can write dp as, well, it should be the square of the scattering amplitude. But this would be a normalized probability if our initial states and our final states are normalized. We have not chosen a unit normalization for our one-particle states and multi-particle states in the free theory, and we're not going to choose we're basically going to choose the same normalization in the interacting theory. So our initial state and final state will not be unit normalized in our interacting theories, and so we need to divide by the norm of our initial state and final state. Okay? So the probability of scattering to a specific final state, where we specified not only the type of particles in the final state, but their momenta precisely, should be 0. So there's usually some continuous parameters we can change. If we collide 2 particles in elastic scattering, they can scatter off in any angle, and the probability they scatter off at a particular angle is 0. So we need a measure here over the momenta of the final particles. So you might imagine there's some product over d3 pj, where pj are the momenta of the final particles. We need to be careful about the normalization here. And we can understand the normalization by compactifying our space. So if we compactify our space in a periodic space, with period L, then the volume is L cubed, and the momenta will be quantized. So the momenta will be 2 pi over L times some vector of integers, vector with integer components. And so in this periodic space, what we would do instead of integrating over the final momenta, we would sum over the final momenta. They'd be discrete. So what we would do is we'd sum over nj. And once we took the continuum limit, these n's are related to p's by factors of 2 pi over L. So we'd get a sum over d3p j over 2 pi cubed, 1, 2 pi for each dimension of space. And then we get a factor of L cubed, which is the volume. So we get times the volume. So here we need to put in a 2 pi cubed times the volume in order to normalize this correctly. Any questions so far? Okay. So, of course.
The volume here, is that the volume of like the entire space or just
The entire space.
And the volume before was the volume of the beam?
Oh, yes. So, okay, so this is the volume where scattering can happen. So it's the region where our particles are overlapping. We'll be considering initial states, which are momentum eigenstates. So they're completely delocalized in position space. So they're basically plane waves. So they do cover all of space. So in a sense, they're the same thing, because before we had a finite region where scattering could occur. If we take our initial states to be plane waves, then the volume is all of space where scattering can occur. Okay. So we can simplify this formula a bit by using some properties of we expect for the S matrix. So S, so this time evolution operator, S is referred to as the S matrix. And we expect it to have two parts. So one part is if we send two initial particles in, nothing can happen. In a free theory, S is just equal to 1. But it's certainly possible we send in two particles and they miss. They just don't interact. In which case, our final state will be equal to our initial state. This is not a very interesting part of scattering. So we're essentially just going to ignore this part and throw it away. We can include it, but it's not interesting. But the interesting part of the dynamics is encoded in what's known as the transfer matrix. So here, this is the S matrix, transfer matrix. And it's conventional just to put a factor of I here. And we expect that the transfer matrix vanishes unless momentum is conserved. We certainly expect momentum to be conserved, and it would be a serious problem if it wasn't. So we expect that the transfer matrix is proportional to a momentum-conserving delta function. And we'll see this explicitly when we calculate examples later, but you might, just based on the idea that we expect momentum should always be conserved, expect this should be proportional to a delta function. And so here P indicates the momenta of the final particles, and I'll throughout today's lecture and most of the subsequent lectures use K to indicate the momentum, for momentum of the initial particles. And so what do we see? If we plug this relation in to our expression for the differential probability, we get that f s minus 1 I squared is 2 pi to the 8th times this delta function squared. And so this FMI is often abbreviated as just m squared or mi to f. So we'll use this notation if the process is understood, or this is just a slightly shorter notation for the same thing. And this quantity here is known as the matrix element. And there should be an I, yes. So IM is known as the matrix element. So thinking about S matrix as big matrix that encodes all the information of how every possible initial state transitions to every possible final state. This is one element of that matrix. It tells us how a particular initial state transitions to a particular final state. So this looks somewhat concerning. We've got here a delta, 4-dimensional delta squared. That's something I told you should never do in the front end, square a delta function, but here I'm doing it. So if we used, we could use one of the delta functions. We did one of the integrals of the delta. The argument of the other one would become 0. So we've got here in this expression basically a 2 pi to the 4th delta to the 4 of 0. We've seen something very similar already in yesterday's lecture, a 3-dimensional version of this. And what we did to save things there was just interpret the delta of 0 as the dimension of space. It was a 3-dimensional delta of 0. Here we've got a 4-dimensional delta of 0. And we did that by just noting that this is the same as this integral e to the I p dot x evaluated at p equals 0. Before that gave us delta 3. It gave us we get rid of this. We just got the volume of space-time in this case, or space from yesterday. So we'll write this as the volume times the time. So again, if we're considering plane waves as our initial and final states, the volume where scattering can happen is the same as volume of space-time, and so it's the time interval. Time is all of time. Okay. Okay, so, what a question? Yes.
Why do we have the I there? The transformation.
The I, it's just a convention. It's the motivation behind it is you could write it as like, so this is a unitary operator, time evolution operator. So you could imagine writing it as e to the I times something Hermitian. And if you just Taylor expand it, you'd have an I here. But this is defined to be exact. So this is not Hermitian in general. That's why somebody at some point put an I there.
How do you relate the last line to dp?
This one?
Yeah, like now that you subtracted the 1 from the s.
Okay, so, well, we're going to see that. So there's several answers we can give. So one is that experimentally, it's very easy to pick out the case where there's no scattering, and you can just subtract that off. So really what we're interested in is just the case where there's non-trivial scattering. We could extract that experimentally. Or we'll see in a few lectures that actually the cases where there's no scattering, we'll have even more delta functions than this. So they'll be, they'll never interfere with the ones we're interested in where there's non-trivial scattering. So we can basically just treat them entirely separately.
Where did the K's go? You know, for the sigma b inside the delta?
Where did the what go?
From like the previous line.
So here, this is just a shorthand notation for all momenta, just so I don't have to write this out explicitly every time. But this means exactly the same thing. So I can write this as sum of I and F, if you like. Okay, so the next thing we need to do is, so we looked at the numerator in dp. Let's look at the denominator. So there we have the norm of I and the norm of F. And remember from yesterday that we normalized our one-particle states. So in the free theory, we normalized our one-particle states so that the norm of a one-particle state is 2 pi cubed 2ek times delta of k minus k. So this is a 2 pi cubed delta of 0, which we'll interpret in exactly the same way as just the volume of space. And we're going to normalize our interacting states in exactly the same way as our free states. So normalize the interacting states in the same way. So that means that our initial state has two particles. So we get one factor of 2ek times the volume for each of the particles. Our two particle states in the free theory would just be, we'd get this factor for each of the particles. So we'll assume it's the same in the interacting theory. So k are our initial particles, and we get the volume squared. And then for our final state, the same thing. We just have n particles. So we've got the product, j equals 1 to n, 2e E j times the volume. So we've got n factors there. So we can combine our results so far. And what we get is that dp is equal to, I'm going to pull the momentum integrals into this thing I'll call d phi, and I'll write a formula for that in a minute. We've got an Im squared. We've got a t from the numerator. So we've got to write it all out. We've got a volume times t from the numerator. We have two ek1, two ek2 from the norm of the initial state. We have a volume squared from the norm of the initial state. We've got a volume to the n from the norm of the final state. And then from the momentum integrals, we have a volume to the n. This is from f. This is from d3p. And so most of these factors of the volume cancel. And we're just left with t over volume. And this d phi is what's known as the phase space measure, or just the phase space. I'll refer to it. And that's everything I didn't write, which is the one delta, the other delta here. So we had two. One was the volume of space-time. The other one is just a momentum-conserving delta function. So this is the sum over all momenta. And then we've got the product over the final momenta. With a Lorentz invariant measure. Okay. So we're essentially done. What we're interested in is the cross-section, which fortunately has factors of t and the volume. So these remaining infinite factors will cancel off. And what we're left with is then d sigma is d phi times Im squared over 2 ek1 2 ek2 times the v. There was a v in our formula up here that related the cross-section to the differential probability. And this v is the relative velocity between the two initial particles. Okay. So this is our final formula for the differential cross-section. Yes.
Good question. What do you mean exactly by d phi is phase space? Like, what?
More precisely, it's the phase space measure. Or that's just the terminology it's given. But so phase space in this context means a slightly different thing from what you're used to. So phase space here just refers to the possible set of final momenta of your particles.
You define the measure of the phase space by.
That's right.
And how do you get the first formula on the first line?
This one?
Yes.
So to get this line, I just start with the bottom formula on this board. and plug in our results for f s minus 1, throwing away the trivial part. And that's related to im. That's where the im squared comes from. That's where, so this, and this delta come from the FSI. This part here comes from the II. And these n factors of the volume and these factors of 2EP come from the FF. The measure I put over here. Other questions? So for decay rates, almost everything works in exactly the same way as before. So there are a few small differences. So the first thing to do is to understand what type of decay rate we're talking about. So the one you're probably most familiar with is the total decay rate, which is just 1 over the lifetime. We have some unstable particle. The decay rate tells us how quickly that particle decays to anything. In order to use the results of the same method we used before to calculate the cross-section, we need to specify a final state. So we can write the total decay rate as a sum over the possible decay channels. And by a decay channel, I just mean a particular set of final state particles. So for instance, so it's a sum over the decay channels of the partial decay width. So for instance, the tau is an unstable particle that can decay to an electron in neutrinos, or it can decay to a muon in neutrinos. And so the total decay rate would be a sum over those decay channels and all the other possible decay channels. And what's easier to compute is the partial decay width. That's what we'll compute. And, well, basically just, we can just do that by analogy. So the differential partial decay rate should just be the differential probability over the time. And most of our work before in calculating the cross-section was in computing the differential probability. Really, the only thing that changes in that calculation is for a decay, we only have one particle in the initial state, which means we'll only have one factor of of 2 EK. So we had one factor for each of the initial particles for a decay rate. For a cross-section, we have only one for a decay rate. But otherwise, everything is exactly like before. So do decay rates in one line, given what we've already learned about, for cross-sections. And so you might worry about putting an unstable particle in an initial state in the asymptotic past. But as we see when we actually calculate these matrix elements, we're going to assume that all of our interactions occur in a finite time, and so it'll all work out.
Isn't there an extra factor of volume that you didn't cancel off now?
Well, we also lose a factor of volume because we only have
Oh, I see.
one
Okay.
one factor of one particle in the initial state.
I have another question. So, how Lorentz invariant is d sigma?
Okay, that's a good question. There are to answer the question depends on how you define V. Different textbooks define it in different ways. So if you just define it in the simplest possible way, that's V2 minus V1. Then this is not Lorentz invariant. It'll transform like a cross section. But cross sections will only change if you do longitudinal boost instead of a transverse. Boost. But other textbooks and most of the experimental results, you'll see define V in a different way that makes everything Lorentz invariant. They define it to be K1.K2 minus M1 squared M2 squared over EK1 EK2. And if you define it like this, these two agree in the center mass frame. This numerator is Lorentz invariant. This will cancel off these EVs. Our phase space is Lorentz invariant. It's a four-dimensional measure, four-dimensional delta function. Lorentz invariant measures. So you can use either one you like. And in practice, we only ever calculate these things in the center mass frame. So you get nicer Lorentz properties if you use this one. And similarly, this is sometimes, so this is not Lorentz invariant as I've written it because of this factor of EK. Our matrix element, I should have mentioned before, our matrix elements are Lorentz invariant. Those are always Lorentz invariants. But if we define this to be this thing evaluated in the center mass frame, then it's Lorentz invariant. And that's often done, too. Then this just becomes the mass. Okay. So we can actually simplify these formulas for the cases we're interested in, which will have where we have 2 or 3 particles in the final state. And we can do that because we can do 4 of the phase space integrals without any knowledge of what the matrix element is. And that's because we've got 4 delta functions there. So we can do those integrals and once and for all and save ourselves a lot of work later. So I'll just show you how that works for the case of 2 massless particles in the final state. So in that case, we often put a subscript 2 to indicate that there are 2 particles in our final state on the phase space measure. And that the phase space measure in this case just becomes the integral, or not the integral, just delta E1 plus P2 minus sum of the initial particles, E3, P1, 2 pi cubed, 2 EP1. And it's easier in every case I know of to evaluate cross-sections and decay rates in the center mass frame. So we go to the center mass frame. Then the total initial 3 momentum is 0. And we can say that the total initial energy is ECM. In this frame, we can simplify this phase space. And to do that, we can do that by doing some of the delta functions. So what we're interested in computing is the integral over the phase space. And we can directly just use the spatial part of this delta function to do the P2 integrals. And that will just set P1 plus P2 equal to 0. So what we get there is we've got 2 factors of 2 pi left over. We've got 4 upstairs, 6 downstairs. And we have 2 EP1, 2 EP2, and 1 delta left over. So that tells us that the final energy is equal to the initial energy. And if the particles are massless, then we have a further simplification. We know that EP1 is equal to the magnitude of the 3 momentum of the first particle, but by momentum conservation, that's equal to the magnitude of EP2, the initial, the initial and final 3 momenta are 0. That's equal to EP2. So this integral of the phase space becomes the integral of 1 over 16 pi squared P1 squared. That's from the EP1, EP2 in the denominator. Then we can go to, got a delta of 2 P1 minus ECM. And we can go to spherical coordinates. So we get a P1 squared d omega dP1. And this cancels. And we can do this integral, again using delta of f of x is the sum over delta x minus xi for f prime xi. F xi 0. So we get a 2, a factor of a half from that. So we've got a 2p1 instead of just a p1. And so this is equal to, and the integral d omega over 32 pi squared. So claim is that these manipulations are unchanged, even if we throw in the matrix element. So that means that So that means that we want to compute integral d phi 2 of some function of p1 and p2, some Lorenz invariant function that's equal to d omega over 32 pi squared f of p1, p2, evaluated at p2 equals minus p1 and p1 equals a half ECM. So none of the derivations we did here will change if we throw in a Lorenz invariant function. And for those of you looking in the notes, depending on when you downloaded them, there may be a minus sign missing in equation 26. So we often abbreviate this relation as just d phi 2 is equal to d omega over 32 pi squared. So we can, the big simplification, we just need to do one angular integral, and one of the two angular integrals is usually trivial. So works. And in tutorial and homework, you'll generalize this to include masses. Any questions on that?
What's the constraint on F? Would that be true?
This?
Yeah.
For this? Nothing. This works in general.
So any function of F.
Any function of f. All we've in this derivation, we've only done delta integrals. So if we had we went from here to here, we had a function f. Just f would go here, and all we did here was we evaluated this at p2 equals minus p1. And so we just do the same thing for f, and similarly for the next step. Okay, so I want to go through an example. We haven't yet learned how to compute the matrix elements, so I'm just going to give you an example of a matrix element to see how we would go through the last steps of once we have a matrix element actually computing the differential cross-section. And to be explicit, I'll give you the Lagrangian and describe the process. So once we learn how to compute the matrix elements, you can go back. And once we do that, it should only take you a few minutes to actually check that this matrix element is correct. And so the theory we'll consider is a toy theory. It's one also discussed in Tong's lecture notes. That describes the interaction of a scalar nucleon with a meson. So rho here is a complex scalar field. Phi is a real scalar field. And they interact via a 3-point interaction where two nucleons and one meson interact. And I'm going to set all the masses to 0 in lecture in the lecture notes, I keep the masses, but just for simplicity, I set them to 0. So these are m equals 0. So this is a simplified version of how nucleons like protons and neutrons interact with mesons, which are bound states of quarks and antiquarks. So the difference between this model and a more realistic model is real nucleons have spin 1/2. We're just doing a scalar version of that, so we don't know how to incorporate spin yet. Tibor will tell you how that works. And real, well, doesn't really affect this calculation, but real mesons are pseudoscalars instead of scalars, which means they behave differently under parity in one of the discrete symmetries of space-time, which I believe also Tibor will tell you more about. This is our model. And let's suppose we're interested in the scattering of two nucleons, then the matrix element, or if we assume the initial momenta are K1 and K2, as we've been doing, and the final momenta are P1 and P2. And the matrix element at leading order in perturbation theory, it's just minus I t squared times. So the Fourier transform of two of the Feynman propagators that we discussed at the beginning of today's lecture. So that's not an accident. We often matrix elements will in general be sums of products of Feynman propagators. So our result.
Isn't that K2? In the last part, K1 minus.
Here?
Yeah. Or is it?
No, it should be K1.
Oh.
Sure. I haven't described how to calculate this, but once we do, ask me again. So the formula for the differential cross-section, this is equal to, we have two particles in our final state. Square the matrix element, divide by 2 Ek1, 2 Ek2. And in this case, we have two identical particles in the final state. So if we integrate it over all possible final momenta, we'd be double counting. There's no way we could distinguish if the first final state nucleon had momentum P1 versus P2. So we need to divide by a symmetry factor here. And just as a preview, when we learn how to calculate matrix elements, we're also going to be discussing symmetry factors. This symmetry factor is completely different from and has nothing to do with the symmetry factors we're going to talk about later. Unfortunately, they have the same name. But this is the origin of this. If you think about the origin of where these symmetry factors come from, you can keep them separate in your mind. This one comes from we don't want to double count when we're integrating over the final momentum. the symmetry factors we'll talk about later when we compute the matrix elements will have a different origin. They're different. And so in order to evaluate this, it's always easiest to work in the CM frame, center of mass frame. In the center of mass frame, our particles are all massless. So if the first particle has some energy E, the second particle has to have the same energy, and the opposite 3 momentum. By conservation of energy, the energy of the final particles has to be the same. Their 3 momentum can be in a different direction. They have to have the same magnitude. So our 4 momenta have to take this form. And so this gives us that d sigma is a half. We've already computed the phase space for massless particles. So we just get d omega over 32 pi squared. We still have Im squared. And these energies are all just E. The velocity is 2. One of the initial particles has velocity plus 1. The other one has velocity minus 1. So we get here 8 E squared. And then in order to compute Im squared, we need to compute the products of K1 with itself, P1 with itself, P2 with itself, and K1 with P2, K1 with P1. So all of the 4 momenta squared is 0 because we're dealing with massive particles. So that's easy. Then we also need to compute the product of K1 with P1, and that's using the explicit forms here, E squared minus K dot P, and similarly K1 dot P2 is E squared plus K dot P. And we can assume that there's some angle theta between K and P. And we know that the magnitude of K and P are both E, so massless particles. So these become E squared 1 minus cosine of theta, and E squared 1 plus the cosine of theta. Any questions so far? We just need to compute the matrix element, and that's e to the 4th, 1 over K1 minus P1 squared plus 1 over K1 minus P2 squared. Which, since a squared is 0, is 1 over minus 2K1 dot P1, 1 over minus 2K1 dot P2. And using our results for K1 dot P2, this is G to the 4th over 4E squared, 1 over 1 minus, this is all squared, cosine of theta, plus 1 over 1 plus cosine of theta squared, which is G to the 4th, 4E squared, 2 over 1 minus cosine squared of theta squared. And so get rid of this 2 and this 4, and we get our final result. So we get the angular differential cross-section, e to the 4th over 512 pi squared 1 over 1 minus cosine squared theta squared. That's as far as we can go here. This differential cross-section blows up when theta is equal to 0. It's not even integrable. And that's because we have massless particles. Massless particles can cause infrared divergences. So if we have, in general, things will blow up with massless particles if the massless particle is collinear, going in the same direction as another particle, which happens if theta is 0 or if they become very soft. So can't proceed any further, but you see in the lecture notes that we get a finite answer, but it's a bit messier if we keep the masses. Yes.
Why aren't we using the epsilons anymore? The definition of R.
So the epsilons are always, they're an infinitesimal parameter that they go to 0, and there's no obstruction here in sending them to 0 right away. So I just set them to 0. Sometimes they'll be important, other times they're not. Okay, so where we're going tomorrow is we're going to learn, take the next step on our journey in learning how to compute these cross-sections. We will relate these matrix elements and scattering amplitudes to time-ordered products of fields. We'll then spend a few lectures learning how to compute. So it's going to be a several-step journey, but that's where we'll go tomorrow, and we'll think more carefully about what we mean by our initial states and our final states. And we'll talk about interacting scalar field theories explicitly. So one thing to note is that in today's lecture, we didn't really use any properties of scalar fields. So today's lecture basically follows if we have, all the results are unchanged if we have particles of spin. Yes?
What are all the factors of energy go?
I probably just forgot to write them. They should be there, yes. E to the 6. Yes. Thank you. Any other questions? Okay, I'll see you in tutorial this afternoon.